Hello, I am Josh Pankratz, and my colleagues and I would like to discuss arc energy, how to consistently measure arc energy, and some parameters used to control the delivered energy into an arc today. Arc energy continues to be important and critical due to the increased process powers, the known relationship between particle size, arc energy, and increased output powers. Requirements continue to be becoming more stringent around allowable particle sizes as the film properties and structures become more sophisticated and feature sizes decrease. The need to better understand arcs and the parameters used to optimize them, and at times control the energy into an arc, become more critical. Today we will discuss arc formation. This is well known, and arcs will occur. The power supply has to be able to respond and control them. Introduction to the phases of the event and the power supply's response. Measuring arc energy, a review of the parameters used in our experiments to control arc energy and our experimental results. During the process, the impedance can be managed as a uniform field along the racetrack, right here. When the arc occurs, the field collapses, becomes a singular point, and that becomes a low impedance path of least resistance. In turn, all of the process current wants to flow through this point, and the power supply needs to detect this change in impedance, react to it, and extinguish the arc. To extinguish the arc, the output current or the current in the arc must be driven to 0 amps, thus interrupting the fault. We're introducing some phases for the arc. There are 5 phases. The power supply arc detection and reaction features are designed to respond to each of these and control them. Initially, the first 2 phases are the formation and the impedance transformation of the arc and the arc burn voltage in the first 2 phases. Phase 1 typically has the impedance change, and depending on the characteristics of the arc and the power supply, that will determine the natural response for the voltage and the current. Detecting and qualifying the arc will ultimately determine the time that the arc is spent in phase 1 and phase 2. Naturally, there are delays in the power supply detecting the arc and hardware delays in the power supply's reaction. Phase 3 here is the time that the power supply is actively responding to the arc. Some supplies simply shut down, turn off power, and the energy stored in the output of the power supply and in the cable are then delivered into the arc. Those will have slightly higher arc energies. Some supplies actively divert the power from the chamber and provide an active voltage reversal to drive the current to 0. Phase 4 is the shutdown time, right here. This is the time to allow the event area to cool, and that cooling of the event area reduces the probability of reforming an arc when power is reapplied to the process. These are typically adjustable times, and the user would want to optimize the timing for each. Phase 5 is the time when the power is returned and the process returns to the intended steady state. Measuring arc energy is challenging. We measured at the chamber, terminal 1 here, and we used a digital oscilloscope and used the math functions to calculate the power and then integrate from 90% of the process voltage to the end of the shutdown time, phases 1 through 4. We also took a number of samples and averaged those together to get an average arc energy. We happen to use 10. You could choose any number if you'd like. All data presented will be from measurements taken at the chamber and using a 7.5 meter triax cable unless we otherwise note it. These 2 pictures are taken at opposite ends of our cable. The top one is taken at terminal 1 The bottom one is taken at terminal 2 at the power supply. And what we see is a 16% reduction of our measured arc energy at the power supply. This is due to the reversal during this time here, where the voltage has reversed sooner than it did at the chamber, and that energy and that time is subtracted from this measurement. And it's actually pulling energy out of the cable. This is just to point out that depending on where you measure, your arc energy, your measured arc energy can vary. So be consistent. For our experiment, we used an advanced energy Ascent SMS DMS AP30 and an Ascent DMS 60. We ran at 20 kilowatts and 18 kilohertz on either aluminum or silicon magnetrons, 1.5 meter rotatables, and we used an argon oxygen atmosphere. Typically, we're running in the poison mode. The experiment varied a number of parameters. We started with the arc detection features. We chose to do the voltage threshold. There are others you could vary as well, and persistence. We also modified the reverse voltage, which is sometimes known as a boost, and the output cable types and lengths. The distributed nature of arc energy has been presented before. However, we found that we can affect the distribution of the measurements. And initially, our measurements were grabbed using 42 samples of our default settings, and we found a Gaussian-looking distribution. Refining the process and measurements and retaking 30 samples reduced the distribution down here. It narrowed the range of the distribution significantly, and it also flattened the distribution out, so it was more uniform. We found that these items that were sensitive to these measurements were the target conditioning, burning in the target, current probes. We started with 150 amp DC current probes on a 60 amp process. That wasn't sufficient. Internal heating over time caused these probes to drift. We ended up replacing them with 500 amp current probes, and that stabilized our measurements significantly. Also, the trigger type, we found variabilities in how we triggered. We started off triggering on either a falling voltage or a rising current. And ultimately, we switched over to a triggering off of the shutdown time. And that also stabilized the measurements. And there's naturally going to be some error introduced because humans are manually finding the cursor placement and determining the 90% of the process voltage. There are a number of methods used to detect arcs. The simplest is a threshold detection, voltage or current, for example. Logically, the closer we are, the closer you put your threshold to where you're operating, the faster the response will be. However, the trade-off could be false detections. Our process voltage was around 320 volts, and the burn voltage or phase 2 was less than 50. So we limited our voltage threshold variations from between 50 and 300 volts. As expected, the arc energy decreased as the voltage threshold was increased here. And an oscilloscope is the best way to optimize the threshold settings, but that is seldom possible in a production environment. Instead, you could use embedded diagnostic tools like Advanced Energy's Fast Act to monitor and optimize your settings. Persistence is sometimes referred to as detection delay. The arc condition must exist at the terminals of the power supply continuously for the persistence time for the power supply to qualify the event as an arc and then respond. The persistence time largely controls the time spent in phase 2. Surprisingly, short persistence times, those below 500 nanoseconds, have relatively flat and constant measurements. It is hypothesized that the distributed nature and the distribution of the arc energies at those lower times are dominant. And it's not until you get above 500 nanoseconds that the burning of the phase 2 becomes more dominant in the arc energy here. Persistence is beneficial for minimizing false detections and controlling the energy into the event. This may be beneficial to add energy, for example, target conditioning, where you're looking to burn off some of the contaminants from the atmosphere. The reverse voltage only occurs in phase 3. You can see the reverse voltage here when the current is being driven down towards 0. Once the power supply qualifies the event and reacts, the goal is to minimize the time it takes to drive the process current back down to 0. An effective method is to apply a reverse voltage to the output during the response. A controllable reverse voltage can be used to compensate for higher process current or longer inductive cabling. Simply, the time spent in phase 3, or the active response time, is determined by the time the power supply takes to drive the process current to 0. This will be dominated by the process and cable inductance, the current differential, and the voltage you're applying across that cable. Using the equation here will help minimize that time, and you can see that increasing your reverse voltage ultimately will drive your delta time down. This oscilloscope capture shows the reverse voltage applied at the chamber and will automatically be removed when the process current reaches 0. The output cable has a dramatic effect on arc energy. We tested 3 output cables and repeated our persistence experiments. We used a 7.5 meter triax, a 4.5 meter twisted pair, and a 20 meter triax. The length and cable type do matter. And unfortunately, the power supply cannot be placed directly on the chamber, and cables are required. And there will be some trade-offs, but you can see here that the 7.5 meter triax actually performed and had the lowest arc energy over even a shorter twisted pair and a longer triax. The difference in the energy was about double. Arc energy can be difficult to measure. The measurement consistency and proper equipment is imperative for comparative analysis. Measure consistently, measure at the chamber from 90% of the process voltage until the end of shutdown, and average a number of samples together due to the distributed nature. And if oscilloscope is not available, use diagnostic tools available with this power supply. The cable type and length are significant contributors to arc energy, and the optimized detection parameters are effective in reducing arc energy. Increasing the thresholds and/or decreasing the persistence times will help. However, you need to balance that with process stability and false detections. Persistence times up to 500 nanoseconds likely do not contribute significantly to arc energy, and you can use the persistence time to help qualify arcs. Controllable reverse voltage is used to drive process currents to 0 and reducing arc energy, largely in the phase 3, the active response of the power supply. And these are effective for high process currents and powers and minimizing the energy contributions from long cables. Thank you. If you have any questions, please contact John or myself at our email addresses, and we'll be happy to engage a discussion with you. Thank you.